This is my 8th video lesson for Unit 13. In this lesson, we'll be calculating the pH of a strong acid and a strong base, and we will analyze the equilibrium constant Ka, Kb, and Kw. Go to page 36 in the class packet. Learning target. At the end of the lesson, I will be able to calculate the pH of a strong acid and a strong base, and to analyze the equilibrium constant Ka, Kb, and Kw. Homework is number 8. For strong acids and strong base, strong means 100% dissociation, which means all ions and no molecule. A strong acid and strong base will completely ionize in solution. Therefore, all the molecules dissociate into ions. Let's first go over how to calculate the pH of a strong acid. Example number 1, calculate the pH of a 0.1 molar solution of HCl. Since hydrochloric acid is a strong acid, it will completely dissociate in solution. This means if there's 0.1 molar of hydrochloric acid, we have 0.1 molar of each ion and no more molecules. To calculate the pH, it is the negative log of the hydrogen ion concentration. Negative log of 0.1 is 1. So the pH of a 0.1 molar of hydrochloric acid solution is 1. For a strong base, how do we calculate the pH from the hydroxide ion concentration? We have to use these two equations. pOH is the negative log of the hydroxide ion concentration, and pOH plus pH equals 14. Example number 2, calculate the pH of a 0.1 molar of sodium hydroxide. Sodium hydroxide is a strong base, therefore it will dissociate completely in solution. This means if there's 0.1 molar of sodium hydroxide, we have 0.1 molar of the hydroxide ion and sodium ion, and no more NaOH. To calculate the pOH, it will be the negative log of 0.1, which is 1. To calculate the pH, we use this equation, and we get the pH as 13. Once you get the pH, you can work backwards to get the hydrogen ion concentration. Here are the lists of the strong acids and the strong base. On the Regents exam, you must be able to identify the strong acids and the strong base. The most commonly asked strong acid is hydrochloric acid, then sulfuric acid, then nitric acid. The common feature in a strong base is an ionic compound with a metal that is bonded to hydroxide that is soluble in water according to Table F. Learning check number 1, A. The pH of a 0.001 molar HCl solution is closest to what? Pause the video, resume as completed. The answer is choice 3. You have to use the equation pH is equal to negative log of the hydrogen ion concentration. Learning check number 1, B. The pH of a 0.005 molar of lithium hydroxide solution is closest to what? Pause the video, resume as completed. The answer is choice 3. You must first calculate the pOH, then from pOH you can calculate the pH. Learning check number 2. The pH of a 0.001 molar of sulfuric acid solution is closest to what? Pause the video, resume as completed. The answer is choice 2. Sulfuric acid is a polyprotic strong acid, which means when each of the H2SO4 molecules dissociate, it gives 2 hydrogen ions. Therefore, if there's 0.001 molar of sulfuric acid, we basically have 0.002 molar of hydrogen ions. To find the pH, we take the negative log of 0.002, which gives us 2.7. For this practice, calculate the pH of the strong acid or strong base. Try to do this yourself. Pause the video, resume as completed. Here are the answers. For weak acids and weak base, weak means less than 100% dissociation. So when a weak acid and weak base are in solution, they do not ionize completely, which means there's a mixture of ions and molecule in equilibrium. Let's say there is 0.1 molar of HF. HF is a weak acid. Since HF is a weak acid, it does not completely dissociate in solution. Notice the equilibrium sign. There is a mixture of molecules and ion. Therefore, the concentration of each of these will be less than 0.1 molar. We will be calculating the actual concentration in the next PowerPoint. Since in weak acids and weak base, there is equilibrium between the molecules and ions, we can write the equilibrium constant for the weak acid and weak base. Let's first write the equilibrium constant for a weak acid. This is known as the acid dissociation constant, Ka. In this equation, Ha is a weak acid. To write the acid dissociation constant, Ka, we had to write the concentrations of the products over the concentrations of the reactants. Notice I left out water because it's a liquid. So Ka is equal to the concentration of the hydrogen ion times the concentration of the conjugate base over the concentration of the acid. The larger the Ka, the stronger the acid. This is because if Ka is a big number, then the numerator is much bigger than the denominator. Therefore, there are more ions. And since pH is dependent on the hydrogen ion concentration, if Ka is a big number, then there will be more H plus ions in solution. So smaller the Ka, the weaker the acid, because there will be less ions. Now let's write the equilibrium constant for a weak base. This is known as the base dissociation constant, Kb. In this equation, BOH is a weak base. The equilibrium constant is equal to the concentration of the products over the concentration of the reactants. Therefore, Kb is equal to the concentration of hydroxide times the concentration of the conjugate acid over the concentration of the base. So the larger the Kb, the stronger the base, because there will be more ions. If Kb is a big number, then the numerator is much bigger than the denominator. Since there's more hydroxide ions, the base will be stronger. And smaller the Kb, the weaker the base, because there will be less ions. Learning check number 3, the ionization constant Ka is expressed as what? Pause the video, resume completed. The answer is choice 4. Learning check number 4. A 0.1 molar acid solution at 298 Kelvin will conduct electricity best if the acid has a Ka value of what? Pause the video, resume completed. You're looking for a large Ka because in a large Ka, there will be more ions, which will conduct electricity better. So the answer is choice 4. Learning check number 5. The ionization constant Ka of all 4 acids are shown below. Which Ka represents the weakest of these acids? Pause the video, resume completed. You're looking for the smallest Ka value, which is choice 1. For task number 3, the water dissociation constant Kw refers to the self-ionization of water. In this equation, when water absorbs energy, it will dissociate into hydrogen ion and hydroxide ion. This exists in equilibrium. So to write the equilibrium constant Kw based off this equation, Kw is equal to the concentration of hydrogen ion multiplied by the concentration of hydroxide ion. Notice that the concentration of water is left out because it's a liquid. Question 2. Is pH dependent on temperature? The answer is yes. With a higher temperature, there is more energy in the system. Therefore, the equilibrium will shift to the right. Since equilibrium shifts to the right when temperature increases, Kw will increase because there will be more ions. And since pH is dependent on hydrogen ion concentration, it would decrease as a result. Question 3. So can a neutral solution have a pH not equal to 7? The answer is yes, as long as the hydrogen ion concentration is equal to the hydroxide ion concentration. Kw is equal to 1 times 10 to the minus 14 at 25 degrees Celsius. Here's the graph of pH versus temperature. So the relationship between Kw and Ka and Kb is that Ka times Kb is equal to Kw, and here's the proof. As you can see, when you multiply Ka and Kb, you get Kw. Here are other constants in the equation. pKa is equal to the negative log of Ka, pKb is the negative log of Kb. pKa plus pKb gives us 14. To figure out the relationship between pKa and the strength of an acid, let's look at an example. Here are two Ka values. This Ka value represents a stronger acid. Let's calculate the pKa. Therefore, the lower the pKa value, the stronger the acid. The higher the pKa value, the weaker the acid. This concludes the video lesson. Remember to do the homework.